The back? All right. Okay. All right. So how many of you had a chance to look at homework 3? No, not yet. So I'll be going over like a couple of concepts in homework 3, and I think this will be like really useful for solving the problems. Okay. So I'm gonna first assume for homework 3 problem 2, I'm going to select my own examples. I'm not going to exactly take it from the homework. So since you guys are in like week 3 right now, so how many of you guys know what Matlab stands for? Like, raise your hands. No one. Like, what is Matlab like? What is the abbreviation? Which is like, what is the shortened form of? What does it expand to? No one? Yeah, that's awesome. So Matrix Laboratory. So that's shortened to Matlab. There's a reason for it, and that's what I'll be explaining it today. And most importantly, so it's important to understand that Matlab is like highly optimized to solve or to perform operations on matrices. So you have industrial jobs still using like Matlab extensively because it gives you speed and flexibility with operations on matrices, and this is like a widespread industrial standard. So let's go on with some of the questions and concepts in homework 3. So let's say, for example, so I'm assuming everyone is familiar with matrix multiplication, right? Okay. So let's say there's an n-dimensional matrix. So in this example, you have A, which is like 2, 5, 10, and 3, 8, 5. So there are like two rows and 3 columns. Right? So in matrix multiplication, let's say, for example, instead A was an n cross n dimensional matrix, right? So it had, let's say, n rows and n columns. And let's say there was a matrix B, which is also n cross n. So if you're multiplying these two matrices, A times B, how many operations do you need to perform? N? N square? Okay, how did you come to that number? How did you come to n? Who said n? Oh, okay. How is it n or n square? I can't hear you, but. Okay, I can't understand your thought process, but how is it n squared? Can you explain? Just a guess. Well, you're actually right. It's n squared. So let's say, for example, um, your matrix was like, let's say A was, here it's 2, 5, 10, and 3, 8, 5. Let's say there's one more row, for example. Let's say, I don't know, 1, 2, 3, or whatever. So this is a 3 cross 3 matrix. And let's say I'm multiplying A with itself, right? So let's say there are two matrices. I'm multiplying A with itself. Let's just call it a different alphabet because it can get confusing. So let's say P. So 2, 5, 10, 3, 8, 5, 1, 2, 3. So each alphabet, each letter, each number here multiplies with a corresponding number here. So for example, let's just take the first row here and the first column here. So there are 3 numbers here, right, and 3 numbers here. So essentially, you have like 3 operations, right? 3 operations to get to one number here. So this will essentially give you 4 times 15, sorry, 4 plus 15, that's 19, plus 10, that's 29, right? So there are 3 operations to, okay, there are 3 operations to get to 29, and there are 9 such elements, right? So there's like, okay, it's more than just 3 because I'm multiplying as well as I'm adding. So this is one operation, and this is another operation, and this is another operation. That's like 3 operations, and I'm also adding them. So it's total of n square operations if you do the math for, so for one variable, it would be like, yeah, it's 4 operations. So it's actually, yeah, so it's 4 operations per element, and there are 9 elements. So you would have like 36, right? So 36 total operations, right?
So it's more like n squared times n plus 1.
Yeah. So it's n, yeah, something like that. So it's more than n squared. So what happens is, in this case, for example, it's just 3 rows and 3 columns. But imagine there was like 1,000 rows and 1,000 columns. You would have like the matrix multiplication leading to, more than 10 to the power of 6 operations, which is a lot, right? And Matlab is really efficient in doing these operations. So that's what we're going to see first. So if I go to Matlab here, OK. So let me just go one by one. In homework 3, problem 2, so here there are like 2 rows and 3 columns. So one of the easiest hacks in Matlab is like, if you have a big code like this, and if you want to run just like 3 rows of operations, and I don't want to run everything, all you need to do is like just select it, and then click on Evaluate Selection, right? Right-click, Evaluate Selection, and it just gives you this, it just evaluates these 3 statements. This is really useful because sometimes when you're writing the homework file, there are scenarios where you don't complete the entire homework, and you just want to check if some statements are correct or not. So all you need to do is select it and just click on Evaluate Selection. So here, it's pretty straightforward, right? So you have A, which has 2 rows and 3 columns, and C, which has 3 rows and 3 columns. So essentially, AC will have 2 rows and 3 columns. So now, one of the questions in the homework was to check if the reverse was also possible. So if AC is equal to CA, right? So to check that again, I'm going to use the evaluate selection. And you can see here that immediately it throws up an error. The reason being that C has 3 rows and 3 columns, but A has 2 rows and 3 columns. So the inner dimensions don't match, right? So that's why it throws an error immediately. And that's exactly what the error says as well. Now, OK, so there are 2 statements here. You can see that A times A and A dot times A, right? So here, let's say, for example, A is, so here it's like a 2-row, 3-column, 2-by-3 matrix. And I'm going to evaluate this. And it throws an error again because A is 2-by-3, and the inner dimensions don't agree because it's 3 and 2, right? But this statement here, that gives you an answer. You can see that. You can see it here, A dot A. So does anyone know what the statement does? Yeah. Yeah, so pointwise operations. So what does pointwise operations mean? It means that, let's say, for example, A is 2 rows and times 3 column. It kind of multiplies each element by element. So here, there will be cases in like the homework and the project where you may have to multiply element-wise. So let's say, for example, instead of matrix multiplication, I want to perform an element-wise element operation. So 2 times 2, which is 4, 5 times 5, which is 25, 10 times 10, which is 100. So you'll find the A dot A having 4, 25, and 100. You can see here. So this approach is like much more, it's less computationally intensive because I'm not doing this multiplication and addition. All I'm doing is just multiplying each number from 2 matrices, right? So it would just have n operations. Because each, let's say n elements are there total, you just have to multiply each together, and you don't have to worry about the addition aspect of it. So it has lesser number of operations. Now, let's say, for example, I create this matrix, right, which is a random matrix. So rand is a function that creates a set of random numbers, okay? And it has like, it's a 1,000 times 1,000 matrix, all right? And I'm going to compute the product of the matrix A with itself. So any guesses how long this would take? Because it's 1,000 times 1,000, so it's going to be a lot of operations. And based on this, it's definitely more than 10 to the 6 operations. No guesses? 2 seconds? Let's just check it out. Wow, it's less than a second, right? So even if you assume that it takes 1 second, so it's able to perform up to 10 to the power 6 operations in 1 second. So computers these days, there's this wave of exascale computing where computers can perform up to 10 to the power 15 operations per second. So that's the level at which we are in right now. So even my laptop, which is like really old, it's like 5 years old, even this laptop can perform like 10 to the power 6 operations in 1 second. And that's like pretty cool in terms of computations, and we have come a long way. So this is for problem 2. And the remaining problems in problem 2 are like really straightforward. It's just multiplication of matrices. And all you need to do is like perform these operations. You have A times C, you just multiply it. And when there is the element-wise product, you just use a dot in between. This is really important because students come back and say, OK, this is a syntax error that I made, and I need points. No, this is actually an error because like each dot in Matlab matters, right? If you change a dot or if you put an apostrophe or something different, the answer entirely changes. So one of the other cool things about Matlab is that it's able to perform these, solve these problems which are similar to problem 3, where you have to really solve this AX equals B problem. So let's say, for example, all right. So when you multiply this A, AX equals B, right? So X is this unknown set of vectors, and the value of this is important, and that's what we need to find, right? And our objective is to get X. So Matlab can do that in just one line. And here, if you try to arrange it, if you try to write it in the equation format, if you try to perform the multiplication and equate it to the right-hand side, you would get the 3 equations in problem 3. Okay? Now, the standard way of solving this is by taking this matrix A to the other side and writing X equals A inverse B, right? So let's try to do this. OK, one important thing. Here A is a 3 by 3 matrix, right? So A inverse should be easy to solve because you can solve it by hand, and that's not a big problem. Imagine if A was like really huge, getting an inverse operation is really, really hard because inverse of a matrix takes a lot of computational resources. So there are easier ways to solve this. And one of the ways that Matlab optimizes this operation, that's what I'm going to show you right now. And so in Matlab, how do you get the inverse? In Matlab, Do you guys know the command to get the inverse? INV? Yeah, I guess a lot of you know about INV, right? So if you just say INVA, you get the inverse of the matrix. Now, so let's imagine, so here I'm again creating a 1,000 times 1,000 matrix. The reason why I'm doing this is to show how fast Matlab is optimized to solve these problems. A 3 times 3 is like pretty easy for like even to do it using a pen and a paper. But 1,000 times 1,000, let's say, for example, the first method, I think this would correspond to problem 3b. So I'm using the inverse operator, INVA, times b, which is that method that I showed you there. And let's see how long this takes. So, OK. So it's solving this problem in like 0.7 seconds, right? Now I'm going to use the shortcut that is prescribed in problem 3a. So the question says use a slash operator. So this is the back operator, and this you have seen in homework 1 as well, right? So this operator is essentially for solving these large matrix problems. And if I perform the same operation here, so it's like 5 times faster, as you can see here. So this backslash kind of speeds up the operation at least by a factor of 5. And this is pretty cool because in real world, like if you have data regarding, let's say, the weather of different cities of United States in a matrix, and you want to solve these problems, MATLAB is like much optimized to do this through its own operator than to actually compute the inverse using that function and multiply it with the right-hand side. So the reason why we use this command over the inverse operation is because this is much faster. So let's say, for example, if I run this again, it will create a different random matrix. Yeah, you can see here that it's always a factor of 2, at least a factor of 2 times smaller. So the regular operation takes like 0.57 seconds, and the second operation takes like 1/3 of the time. All right, so that's problem 2 and problem 3. Any questions before we go ahead? No questions? Cool. So let's go to numerical differentiation, which is problem 4. OK. OK. So forward difference is like one of the methods used to compute derivatives, right? So in the question there, for example, I think you have OK. So there is cos x times e to the power sin x, right? Instead, I'm going to use a similar example instead because I think the procedure is the same, so I'm going to use f of x as sine x times e to the power sine x. So let's say, for example, f of x equals sine x times e to the power sine x. Right? So one of the ways that you can use Matlab to compute derivatives, which is df dx. So let's say, for example, so f of x has this particular variation, let's say. And we are going to choose 2 points here. This is xn and xn plus 1. Okay? And this point here, if I have to get the value of the function at this point, this would be f of xn plus 1, right? And this point would be f of xn. So we all know that df dx is essentially the slope of the curve, right? So if you have to compute the slope of the curve, so in Matlab, you can assume that for very small variations between xn plus 1 and xn, right? Let's say these two are really, really close to each other. If that was the case, then one can assume that this line here is a straight line, right? For very, very small differences between xn plus 1 and xn, these two values are going to approach each other, and these 2 points are going to be really, really close by, so that you can approximate these 2 points and connect them by a straight line. So if you do that, now f of x, df dx, which is the slope, right? I'm getting the slope of the line. And the slope of the line is basically the difference in the y values, right? fn plus 1, fxn plus 1, minus f of xn divided by this difference in the x values, which is xn plus 1 minus xn. Okay? So this method is called forward difference method. And that's what you're asked to use in problem 4. So let's say, for example, in the problem 4a, you're asked to create a vector x which ranges from minus pi by 2 to pi by 2, right? Note that the step is pi over 100, which is pi over 100. Pi is like 3.14, right? So pi over 100 is 0.03 approximately. And that's a really small value compared to the values of x, which are like 3.14ish. Because remember one of the assumptions that we made here is we assumed that these two values are really close by, which means the step, this pi over 100, is like much smaller compared to the values of x that we are computing. So the way we do this is we first declare x to vary from minus pi by 2 to pi by 2, which is the part A of the question. And then we compute f. How do we compute f? First, we evaluate sin x, and then use a dot multiplying product. So remember, the element-wise product is really important here, because if you use this operation instead, it's going to give you like an entirely different answer. You need a dot over here because you need to multiply each value of sin x with the corresponding value of the exponential of sin x. Okay? And once you do that, you can get f. And let's do that first. So evaluate selection. One second. Okay. So I have f. So I have x first. X is a single row, 101 column matrix, and f of x is also of the same dimension. So this is one of the checks to make sure that it is doing an element-wise operation. And once you do that, you need to use this function diff. So the function diff essentially computes the difference between successive products. So for example, let's say f was equal to 1568, then diff of f would give you, so diff of f usually has a lower dimension than f. So if f has 4 elements, the diff of f will have 3 elements. And the first element here would be 5 minus 1, which is 4. The second element would be 6 minus 5, which is 1. And third element would be 8 minus 6, which is 2. Okay, so what is the diff function doing? It is essentially subtracting subsequent elements of the vector and assigning it to a different vector. So if you, for example, if you want to check out diff, yeah, so diff of x for a vector x is x2 minus x1, x3 minus x2, and similarly xn minus xn minus 1. And the key detail here, which is important, is that the number of elements in diff of f is one short of the number of elements in f. So if this is 4, if f has 4 elements, diff of f has 3 elements, right? Because you can't have, so you need successive elements to compute this difference. So essentially, to find the derivative, all you need to do is, again, notice that in this line, I have a dot divided by. Because each difference of f, I need to divide by the corresponding difference of x, right? So this is in line with the formula that I wrote there. So let's compute that. Yeah. So once I do that, I can see here that it creates this new element, which is 1 times 100 instead of 101, right? So it's 1 smaller than the value, the dimension of f. Okay. So any questions in the forward difference method? This is really important because you will be using this to solve more complicated problems later. In fact, whatever you learned today, right, if there's something that you can take away from this entire class, it would be matrix multiplication and the integration and forward difference. So this is like the most important part of this entire class, to be honest. Okay. So the last part of this thing is trapezoidal formation. So now you know how to find the differentiation, how to perform differentiation, right? So differentiation is approximated using that method. You can see that you need to perform two operations, two diff operations, and you can essentially get the derivative of any function. So note that this is an approximation again, and one of the caveats here is that we need to make sure that the difference between the x's is like really, really, really small. If these values were really apart, the derivative would be a very bad approximation for the curve. So if for example, if these values were really far away, you would essentially be approximating this entire curvature of this function with a straight line, and that's incorrect, right? So that's the most important thing here. Now moving on with the integration part of it. Okay. Okay. So let's say g of x is sine x. Now, the question 5 asks for computing the integration. So just like you did differentiation, right? What did you do in differentiation? You kind of assumed that you kind of split the entire f of x into small blocks where xn and xn plus 1 are really close to each other. The same thing is true for integration as well. So let's say, for example, sin x looks something like this, right? Okay. So during integration is same as finding the area under the curve, right? Just like differentiation is same as finding the slope of the curve, integration is finding the area under the curve. And the question is essentially asking us to find the area which is bound by g of x with the x-axis. Okay. So in the lecture, one of the methods that was suggested was the trapezoidal formation, right? So what is trapezoidal formulation? So was this covered in the lectures yet by the professor? He has covered it. Okay. So I'm assuming that you know that in order to compute the area under the graph, we kind of approximate these slabs to be trapeziums, right? So let's take this to be a trapezium and enlarge it over here. So if you do that, this base, which is xn plus 1 minus xn, that's the base, right? The height is, so this would be g of xn, and this is g of xn plus 1. So the idea here is you're trying to approximate the entire curve into small trapeziums, and you're finding the area of this trapezium, and you're adding it up. Once you do that, you get an approximate estimate for the area under the curve. The error in this formulation comes in this region, right, where you're approximating this. So you're essentially ignoring regions which are in between this straight line and the curvature. So to reduce the error, one needs to assume that xn and xn plus 1 are very close to each other, just like you did in the previous example. So if you do that, in the question, so they're asking for a vector which is z, and this z is varying from -1 to 1 in steps of 0.01, right? And once you get that, you need to obtain g. So I should have used z instead. So g of z would be equal to simply sine of z, right? In the question, it's a more complicated function. It has a hyperbolic sign. So you need to use sine h and sine h square and sine power 4, right? And once you do that, one of the other ways to initialize z would be using line space. Line space is a different function, but it does the same job. It creates 100 values between -1 and 1. And that's the same as creating a vector from -1 to 1 with a space of 0.01, because there are 100 values by definition, right? Oh, yeah. OK. Yeah, I misspoke. So that would be 200 values here. And probably can do the same thing here. So yeah, I think this would be closer to the answer. Yeah, it's a nice catch. So once you do this, essentially in Matlab, there's already a function that can directly find the area for you. You don't need to use the sum function. But in the question, it specifically asks for you to use the sum function. So definitely for the homework, you need to do that. But then there's a command, trapz, which this is the command which can take in the input values, z and g, and give you the area under the graph. So these are the inputs. And the output would be the area under the curve. So let's take a look at. Yeah. So you can see here that trapz is trapezoidal numerical integration, and it approximates the integral of y, right? So essentially, this is the best shortcut to, instead of actually trying to perform the summation operation, you're essentially trying to circumvent that and then use the trapz operation. Both of them would give you the same answer if you try it out. I urge you to try it out. But for the homework, you guys can just stick to this line number 9, right? OK. All right. So in homework 3, the last question involves loading a file, right? So one of the advantages with Matlab is that you can interact and like save your workspace every time you kind of access it. So if you want to, let's say, for example, write a file, like however long it is. Let's say, for example, I want to save the values of G and Z in this program to a file. I can do that using using a MATLAB's inherent format. So MATLAB, by default, saves all the variables in a .mat format. So if you try to, for example, let's say I want to save this variable z. So all I need to do is I need to use this function save. So the save command so the save command, you need to specify the file name and the variables. So in here, for example, if I want to just save the variable z, I need to give the save command as save, let's say, for example, test.mat. That's the file name that I want to save. And I need to give the variable z. Sorry. Let's say, for example, if I didn't evaluate it. OK. Yeah. So if you see here, for example, if I execute this command here, you find that there's a test.mat here. And this test.mat contains the variable z. So one of the ways you can check that is by using, so let's clear the workspace first. And let's say there's no variables here. And I do a load test.mat. Once I click on load, you already see that automatically the variable z is found in the workspace. So you need to use a similar operation for question 6, where there is already a file given. So all you need to do is like load the file name .mat, and it will automatically give you the variable on the workspace. So any questions? No questions? OK. No. So as an aside note, you need to just submit the homework3.m. You don't have to submit any mat file or anything like that. So just a single file for submission, right? That makes it easy for the graders to grade. Yeah. So if you don't have any other questions, then we'll see in the next class. Yeah. What's that?
Within the homework 3, it gives us a download for a file like that. We need to use that. So.
Yeah. Yeah. Just 1 second.